Yes, good morning, Poon and all. Okay, so last class we have seen that the what is the working principle of corona discharge, or what is the main reason behind in electrical power system corona will be happen. Okay, so corona discharge, it is a phenomenon in which because of the ionization process, air medium present surroundings to the overhead transmission line conductors, it will turns into a conducting material or conducting media. So because of that overhead transmission line operates at a high voltage. Okay, so electrical current will tries to flow through this ionized air medium present surroundings to the overhead transmission line conductors. Okay, so it will creates the violet glow or arc surrounds to the live conductors or uh, sharp edges, or we can say that corners or nut bolts of the insulators, etc. Okay, generally the corona discharge will occurs in a electrical power system at a sharp edges. Okay, at and above the uh, breakdown strength of air medium present surrounding to the overhead line conductors. Okay, so last class we have seen that working principle. Okay, so today we will see that important terms related to the corona discharge. Okay, so as I said earlier, corona phenomenon plays an important role in design of an overhead transmission line. Therefore, it is profitable to consider the following terms much used in the analysis of corona discharge. Okay, or the corona effect. So, first and most important terms related to the corona discharge is critical disruptive voltage. Okay, so today's class we will see that various important terms related to the corona discharge. Out of that one, critical disruptive voltage. Okay, so the critical disruptive voltage can be defined as or stated as like this. Okay, so it is the minimum phase to neutral voltage at which corona discharge occurs. Okay, critical disruptive voltage काय आहे? हे एक मिनिमम फेज टू न्यूट्रल व्होल्टेज आहे, म्हणजेच फेज व्होल्टेज आहे. त्या मिनिमम व्होल्टेजला करोना डिस्चार्ज हा दिसून येतो किंवा ऑकर्स होतो. ठीक आहे. सो consider a two conductors of radius r centimeter and spaced d centimeter apart from each other. Okay, if capital V is the phase to neutral potential or the voltage, then potential gradient at the conductor surface is given by, okay, small g is equal to into square bracket capital V divided by R into log E, small bracket D by R, square bracket closed. Okay, so potential gradient. So potential gradient, it plays a very important role while deciding the critical disruptive voltage. Okay, so potential gradient, it will use you the idea whenever the uh, air surrounding to the live conductor get ionized. Okay, based on the value of potential gradient or voltage distribution over the surface of the live conductors decides the um, critical disruptive voltage. Okay, so critical disruptive voltage can be found with the help of potential gradient. Okay, so in order to that the corona is formed, the value of g, small g, must be made equal to the breakdown strength of air. As I said earlier, potential gradient will plays a very important role while deciding the voltage distribution around the live conductors. Okay, if we made the potential gradient equal to breakdown strength of the air medium presents to the uh, surrounding of live conductors, at that condition the corona discharge will start. Okay, मला काय म्हणायचंय बघा की पोटेन्शियल ग्रेडियंट ही एक खूप इम्पॉर्टंट कन्सेप्ट आहे की पोटेन्शियल ग्रेडियंट हे व्होल्टेज डिस्ट्रीब्युशन दाखवतं सराउंडिंग टू द लाईव्ह कंडक्टर. ओके, पोटेन्शियल ग्रेडियंट जेवढा जास्त असेल ओके तेवढं काय होईल आपलं क्रिटिकल डिस्ट्रक्टिव्ह व्होल्टेज जे आहे त्याची व्हॅल्यू त्याच्या प्रोपोर्शनल मध्ये चेंज होईल. ठीक आहे, तर पोटेन्शियल ग्रेडियंट म्हणजे दुसरं तिसरं काही नसून काय असतं ते व्होल्टेज डिस्ट्रीब्युशन राउंड द सरफेस ऑफ लाईव्ह कंडक्टर्स. ओके, आणि सपोज जर कॅपिटल व्ही हे फेज टू न्यूट्रल व्होल्टेज असेल किंवा फेज व्होल्टेज असेल ऑफ द ओव्हरहेड लाईन आणि आर ही रेडियस असेल लाईव्ह कंडक्टरची आणि डी ही स्पेसिंग असेल, जर फेज कंडक्टर मधली स्पेसिंग असेल डी सेंटीमीटर, तर आपण पोटेन्शियल ग्रेडियंटची व्हॅल्यू काढू शकतो. जसं की स्मॉल जी इज इक्वल टू व्ही बाय स्मॉल आर इंटू लॉग ई small d divided by r, which is measured in volt per centimeter. Rotation gradient is measured in volt per centimeter. Okay, so corona discharge will happen whenever a potential gradient across the conductor which is equal to the breakdown strength of air medium present surrounding to the live conductor. Okay, so as we know that the breakdown strength of the air at normal temperature pressure condition is 30 kilovolt per centimeter or 21.2 kilovolt per centimeter RMS value and is denoted by the G0. Okay, potential gradient. Okay, potential gradient whenever equal to breakdown strength of the air, at that condition corona discharge will happens. Okay, we know that at normal temperature pressure condition the potential gradient is denoted as G0. Okay, denoted as G0. Okay, if Vc, capital V to the suffix small c, is the phase to neutral potential required under this condition. ओके, जेव्हा म्हणू आपण की नॉर्मल टेम्परेचर प्रेशर कंडिशनला पोटेन्शियल ग्रेडियंट जे काही असेल त्याला आपण G0 म्हणू आणि या G0 ची व्हॅल्यू ही सपोज फेज टू न्यूट्रल व्होल्टेज Vc आहे, तेव्हा आपण अशी काढू शकतो G0 इज इक्वल टू capital V to the suffix small c r into log e d by r volt per centimeter. Okay, हे potential gradient असेल at normal temperature pressure condition. Okay, but there is no always normal temperature pressure will be there at the overhead transmission line. Okay, the normal temperature pressure it will be changes based on the atmospheric condition, climatic situation, depends upon the season. Okay, so where G0 is nothing but what? Breakdown strength of air at normal temperature pressure. Okay, but G0 is nothing but what? Breakdown strength of air medium present surrounds to the live conductor. Okay, at normal temperature pressure breakdown strength of the air is treated as a potential gradient. Okay, whenever the phase to neutral voltage is Vc. Okay, so from this above formula, okay, G0 equal to into square bracket capital V to the suffix small r, capital V to the suffix small c divided by r into log to the base e d by r volt per centimeter. Okay, where G0 it is the breakdown strength of the air at normal temperature pressure. Okay, so from this equation Vc is nothing but what? Critical disruptive voltage can be found from the equation number 2. Okay, so critical disruptive voltage Vc is equal to what? G0 R in G0 into R log E d by R. Okay, remember that expression for the critical disruptive voltage VC. It is phase to neutral potential or phase to neutral voltage. Okay, or phase to neutral potential difference at which the corona discharge is just start to happen. Okay, that is nothing but what? Critical disruptive voltage. Okay, परत एकदा सांगतो मी की क्रिटिकल डिस्ट्रक्टिव्ह व्होल्टेज म्हणजे असं मिनिमम फेज टू न्यूट्रल व्होल्टेज आहे की ज्या व्होल्टेजला करोना डिस्चार्ज हा हॅपन व्हायला सुरुवात होते किंवा करोना डिस्चार्ज हा दिसून येतो त्या व्होल्टेजला किंवा त्या पोटेन्शियल डिफरन्सला क्रिटिकल डिस्ट्रक्टिव्ह व्होल्टेज म्हणायचे आपल्याला. ठीक आहे, क्रिटिकल डिस्ट्रक्टिव्ह व्होल्टेज. ओके, next the above expression. Okay, the above expression for disruptive voltage is under standard condition. Okay, above expression is for the under the standard operating condition, or we can say that at normal temperature pressure condition. Okay, however this disruptive critical voltage or critical disruptive voltage VC may vary with climatic condition like air density. Okay, also going to change the uh, value of potential gradient G0. Okay, means what? Indirectly critical disruptive voltage will be depends upon some climatic condition like air density. Okay, so the value of G0 is proportional to air density. Okay, thus the breakdown strength of the air at a barometric pressure B of mercury and temperature of T degree centigrade become a delta G0, where a delta is air density factor. Okay, बघा की आपल्याला माहिती आहे क्रिटिकल डिस्ट्रक्टिव्ह व्होल्टेज व्ही कॅपिटल व्ही टू द सफिक्स स्मॉल सी इक्वल टू G0 into R into log E into bracket D by R. Okay, where G0 is nothing but what? Potential gradient at normal temperature pressure. But potential gradient, it will vary and according to the climatic condition like air density. Okay, so how the air density will going to affect on the potential gradient? Potential gradient will be proportional to air density, proportional to air density. As we know that critical disruptive voltage is proportional to uh, potential gradient, and potential gradient is proportional to air density. So we have to consider the air density factor. Okay, so air density factor we have to consider. Okay, so air density factor delta can be defined like this: 3.92 B divided by 273 plus T degree centigrade. Okay, where air density factor delta is equal to 3.92 into B divided by 273 plus T degree centigrade. Okay, where B is what? It is the barometric pressure, and where T is nothing but what? It is the temperature of ambient or temperature of atmosphere. Okay, so finally we can write like this: critical disruptive voltage considering the air density factor, we can write like this: equation number 4, capital V to the suffix C is equal to G0 into delta into R into log E to the base E into bracket D by R. Okay, let it equation number 4. Okay, so equation number 4, VC is equal to G0 into delta into R into log to the base E D by R represents the critical disruptive voltage considering the air density factor delta. Okay, so once again I will repeat: critical disruptive voltage is nothing but, I'm sliding my arrow pointer, look at this one: critical disruptive voltage considering the air density factor delta is equal to capital V to the suffix small c is equal to Z0 delta R log E to the base, log to the base E by R. where G0 is what? Potential gradient at normal temperature condition or at standard condition. Delta is nothing but what? Air density factor. Okay, air density factor. R is nothing but what? Radius of the live conductors. Okay, log to the base E, small d by R, where d is nothing but what? Spacing between the phase conductors. Okay, spacing between the phase conductors. Okay, remember that this is the equation number 4, and it is what? It is the critical disruptive voltage considering the air density factor. Okay, so similarly, air density factor affects on potential gradient, and potential gradient will going to affect on critical disruptive voltage VC. Okay, so uh, since we know that uh, surface of the live conductor is irregular, okay, because of we are going to using the ACSR conductor. Okay, so surface is not look like a polished surface. Okay, so irregularity of the live conductors is there. Okay, so the correction must also be made for the surface condition of the conductors. Okay, of the conductors. Okay, this is counted by multiplying the above expression by irregularity factor small m's to the suffix 0. Okay, since have told already, surface condition of the conductor also going to affect on the corona discharge, or indirectly it will affect on critical disruptive voltage. Okay, so if we consider that irregularity of that conductor surface, uh, critical disruptive voltage can be given by multiplying a irregularity factor. Irregularity factor can be defined as small m to the suffix small m to the suffix 0. That is what? M0. Okay, or by considering this irregularity factor of the surface of the conductor, critical disruptive voltage VC can be given by equation number 5. I'm sliding my arrow pointer. Look at this one. Capital V to the suffix small c, which is equal to M0 Z0 delta R log to the base E d by R, kilovolt per phase, kilovolt per phase per centimeter. Okay, where M0 is nothing but what? Irregularity factor. Z0 is nothing but what? Potential gradient at normal temperature pressure, and delta is what? Delta is nothing but the air density factor, which is given by 3.92 into V divided by 273 plus small t. Okay, air density factor. Okay, where M0 is nothing but what? Irregularity factor of the surface of the live conductors. Okay, M0 is equal to 1 for the polished surface. Okay, whenever the surface of the live conductor is neat and clean and smooth and polished surface, at that condition, uh, irregularity factor of that particular conductor will be 1. Okay, for the polished surface, irregularity factor will be 1. Okay, and for the dirty conductors 0.9 to 0.992. Okay, for dirty conductors. Okay, and for the stranded conductors 0.87 to 0.8 for stranded conductors. Okay, this is the value for the irregularity factor of surface of the conductors. Okay, based on the surface of the conductor, whether it is polished, whether it is dirty, or whether it is dirty or standard conductors or ACSR conductors, based on that one, uh, irregularity factor going to change. Okay, so once again I will repeat the final equation for the critical disruptive voltage capital V to the suffix small c will be M0 Z0 delta R log to the base E D by R, which is measured in kilovolt, which is measured in kilovolt. Okay. So I hope all of you clear about the critical disruptive voltage. We will see that next important terms used in a critical or used in a corona discharge is visual critical voltage. Okay, similar to that of the critical disruptive voltage, another term is also used in corona discharge, that is what visual critical voltage. Okay, so visual critical voltage, it is also a minimum phase to neutral voltage at which corona glow appears along the line conductors, appears along the line conductors. Okay, appears along the line conductors. It has been seen that in case of parallel conductors, the corona glow does not begin at the disruptive voltage VC, but at a higher voltage VV, called as a visual critical voltage. Okay, so visual critical voltage in case of parallel conductors. Okay, then in case of parallel conductors, okay, the corona discharge will not be appear along the line of line conductors at critical disruptive voltage, but it will be appears at normally higher than that of the critical disruptive voltage, called it as capital V to the suffix small v. Okay, so that capital V to the suffix small is called as visual critical voltage. Okay, critical disruptive voltage and visual critical voltage is differ from each other. Okay, in case of parallel overhead conductors, uh, the corona discharge will not be appear at critical disruptive voltage, but it is appear normally at higher voltage than that of the critical disruptive voltage. That higher voltage is denoted as capital V to the suffix small v. That capital voltage to the capital V to the suffix small v is called it as critical disruptive voltage. Called it as critical disruptive voltage. Okay. The phase neutral effective value of visual critical voltage is given by following empirical formula. Similar to that of the critical disruptive voltage, where some part is added. Okay, for the visual critical voltage. Okay, so see over here, I will make the comparison between the critical disruptive voltage and visual critical voltage. Visual critical voltage can be given by capital V to the suffix small v, which is equal to m0 g0 delta into r into bracket 1 plus 0.3 divided by under root of delta into r, okay, into log to the base e into bracket d by r. Okay, so this is the formula for the visual critical voltage VV. Okay, so visual critical voltage and critical disruptive voltage is differ from each other by the factor into bracket 1 plus 0.3 divided by delta into under root of delta into r. Okay, I'm sliding my arrow pointer over here. Critical disruptive voltage and visual critical voltage, both terms are near about same, but their values are different. Okay, so critical visual critical voltage is always greater than that of the critical disruptive voltage. Okay, in case of parallel overhead transmission line, corona discharge will not be appear at critical disruptive voltage, but it is appears at just higher than that of the critical disruptive voltage. That higher voltage can be denoted as capital V to the suffix small v, and it is called it as visual critical voltage. Okay, that visual critical voltage, it is greater than that of the critical disruptive voltage by the factor of under root, sorry, into bracket 1 plus of 0.3 divided by under root of delta into r. Okay, where M0 is the irregularity factor having value of 1 for polyester conductors and 0.7 to 0.82 for the rough conductors. Okay. AC power supply system generation and distribution. Okay. So these are the two important terms which is used in the corona discharge. Okay, used in the corona discharge. Okay, I think these two terms like critical disruptive voltage and visual critical voltage is very much important. We have to remember these two terms. Okay, uh, based on these two formulas, there is some numericals we have to solve on the corona discharge. Okay, so be remember that based on the critical disruptive voltage and the visual critical voltage. Okay, we have to solve some numericals on that one. So uh, uh, for the sake of numerical example, we have to go thoroughly through the uh, critical disruptive voltage and visual critical voltage. Okay, both these two terms are measured in kilovolt per phase or kilovolt per phase per centimeter. Here comparison between the visual critical voltage and critical disruptive voltage is that visual critical voltage is always greater than that of the critical disruptive voltage because of, in case of parallel overhead transmission line or parallel overhead conductors, the corona discharge will not be start or appears at the critical disruptive voltage, but it is appears just or higher than that of the critical disruptive voltage. Okay, so that higher voltage value is nothing but what? Visual critical voltage. Okay, visual critical voltage. So remember that visual critical voltage is always greater than that of the critical disruptive voltage, always greater than that of the critical disruptive voltage. Okay, so thank you one and all. I think all of you got the clear idea about the critical disruptive voltage and the visual critical voltage, and what is the difference between the critical disruptive voltage and visual critical voltage. Okay, so today we will stop over here. Thank you with joining with me. Okay, thank you. Today we will stop over here. Okay, thanks.